So I will post exam 3 on my website. I will mention later, when is it? I mean, due dates are very flexible here. Just do all. All right. So again, right? So several properties for the integral. So yeah. So with the exam, I will again. I mentioned about the exam is that it's on the My Open Math, so you should be registered for it. It's not run by me. So be prepared to submit it when necessary. It will be between Wednesday and Thursday. Whenever you open it, you have 3 hours to complete the exam. Make sense? So it's between somewhere in Wednesday morning, I think, and maybe Thursday night. And you have 3 hours from the moment you open the exam.
Professor, on My Open Math, there's one practice final, or I think it's a practice final that I did, but I couldn't find the old finals on there.
Yeah, to be honest, I haven't opened once to look at this website. Not once, right?
Oh.
I just know it theoretically, right? So you have to make an account, you have to be registered, you have to put all that information that Professor Jeff Suzuki has been sending you. I forwarded one of those messages, I think. I can do it again. All right, so back to the material. Back to the material again, comparison properties of the integral. Clearly, if the function is non-negative, the integral from a to b f of x dx is non-negative. Again, guys, if you understand that the integral, although it looks fancy and kind of limity and all noble like this, but it's really nothing more than a sum, right? It's just a limit of a sum, and it inherits all the properties that sums have. And what in particular is it? It's a rectangle whose width is dx and height is f of x, so it tells you are adding areas. So clearly, you can imagine you're adding positive areas. It will be bigger than 0 if the height is positive, yes? Now, by an obvious same reasoning is that if f of x is bigger than g of x, then the integral of f of x is bigger than or equal to the integral of g of x. And you can prove it using property 1. You can simply take f minus g and integrate that. F minus g will be bigger than 0. Right, and then the integral is bigger than 0, but the integral is linear. In other words, you can break it apart. You understand what I'm saying? Linear. Linear is that the integral of f minus g is the integral of f minus the integral of g. Do you follow me, guys? Yes. So then another thing, right? So if a function fx is between little m and big M, in other words, this is a bigger number than any fx, and this is a lower number than any fx, then the integral from ab of fx dx is smaller than capital M times b minus a, because it's like we have a big box that contains the curve f of x here, and its area is big height times b minus a, and the entire region under f is containing the small box M. So M times b minus a is a smaller area, okay? And here is an example of how you can use this idea to perhaps very grossly estimate the integral. So let's say this integral you cannot solve by any means that we have learned. It's actually an important type of integral because it relates to the normal distribution. So this is just a piece of the normal distribution, right? E to the minus x squared, and that's a transcendental type integral. It cannot be described using elementary functions that we have learned, using finitely many elementary functions we learned. So what we can do is this, right? So e to the minus x squared, it looks like a bell-shaped curve, and the height of this, the biggest value it takes, is at 0, at x equal to 0. So that's the biggest value, and the smaller value it can take is at x equal 1. So we have this bounds, right? So it's bound between e to the minus 1 and 1. So this integral is between e to the minus 1 multiplied by 1 minus 0 and 1 multiplied by 1 minus 0. Okay, so other things I possibly wanted to show you is, again, right, remember when you studied related rates or just other questions, right? So you can very quickly calculate the elementary volumes or elementary areas. Okay, so here is an example of trying to do that for the circle of radius r. If you happen to know that the circumference is 2 pi r for any circle that has radius r, then you can use integration to figure out what's the area inside of the circle.
Right.
Yeah. And how do you do that? So here is how I thought of it. So you can imagine that this disk is made out of many, you can call them annuli, I suppose, right? So there are many rings, concentric rings around the origin, okay? And then look at this ring, right? So at any particular ring of radius r, so a ring of radius r, I can cut it here. Let's say thickness is going to be dr. Thickness is dr. So the area in this ring, I can cut this thickness and I can flatten it. It's the, if I cut it, I flatten it out, I get a rectangle, right? The length of that rectangle is 2 pi r for this little r, and the width is dr. Are you following me, guys? So if I make, so you can imagine that this disk is made of many concentric annuli. The annulus at radius r, I can cut it and flatten it. I can produce a rectangle 2 pi r dr, which means that the full area is the summation of those pieces. Full area is the sum of those pieces, which is how I get integral from 0 to r. That means integrate over all the rectangles that you count from 0 all the way to capital R of areas of the form 2 pi r dr, which is those pieces. Make sense? So then you have to calculate this area. Yes, yes. So you see this, guys? From 0 to r. And then you can factor out the 2 pi because it's just a constant. And then you have the integral from 0 to r dr. And that we can solve even using our tools. We haven't learned anything too difficult yet. We know that the integral from 0 to r of r, I can use Riemann sums. Let's say right-hand Riemann sums. And I will get that this equals to, I actually accidentally switched from capital R to little r. It would be equal to capital R squared over 2 times 2 pi will be pi capital R squared. Understand? That's because what you do, you can apply Riemann sums and you can figure out what this thing is as we trained. We are actually going to learn a shortcut, so you don't even need to apply Riemann sums to figure it from there. But the main thing that you want to understand if you want to use integration, effectively, is that it's a sum and how to quickly see. Look, I was working here and right away figure out what integral, how to set it up. Setting up is very crucial. Right, and you see, what this is saying is just summation of all those rectangles, of this type, 2 pi r dr. Sum them up and you get the area of the circle. Okay, so here is another problem. Okay, so suppose you wanted to find the volume of a pyramid. And how can you imagine the volume of the pyramid? You want to imagine the volume built up of objects, a sum of whose volume is the volume of the pyramid roughly. And those objects have to be simple, right? So they are simple enough for you to be able to calculate volume rapidly. Does it make sense? So when you look at a pyramid, and actually some of them do look like that's how they were constructed, what I imagine is just a series of stacked boxes from the base box all the way to the top, and the boxes are very thin. They are very, so this thickness of the box is very small. Make sense? So a typical box, I imagine a box from the top to the bottom has thickness dz, right? And has those dimensions: the red dimension, or the green dimension, and the blue dimension here that I wrote, right? The x and the y. Okay, parallel to the b is y, parallel to the a is x. So then I can simply do proportionality. What I can do is I can observe that, for instance, y over z is the same as, because this is one half of b divided by c, because I just have a right triangle that I draw here. So I draw a right triangle along this plane, and I have y over z is 1/2 b divided by c, which is b over 2c. So I know right away that z, so that y equals to b over 2c z. That's what I know here, right? I can do a similar calculation to figure out that x equals to a over 2c z. And then I have the volume of this box at position Z is simply 2 times A over 2C times 2 times B over 2C is Z, right? Yes.
So when you say similarly X over Z is equal to so-and-so, you're just saying from a different perspective when you're looking at
What
it.
I'm saying is, how do I see it right away? If you do cross-sectional cuts, you are going to see triangles, right? So if I cut like this, if I cut through the Z-axis and I cut through the X-axis, I will cut half of A, right? I'll have this right triangle, which is half of A, and its base is C. If I think of it as this is my base, and half of A is the width, right? So then what do I see? Then I see that that X, look, this right triangle, X divided by Z, this X divided by the Z is the same thing as half of A divided by C.
I understand.
Okay? So I do this, and then I do the same thing with respect to B, and I have the corresponding proportions. So look what I then get. I then get that the volume of the box of the thin box at position Z is AB divided by C squared times Z squared. That's times dZ. So AB divided by C squared times Z squared dZ is the volume of the box at suspended at elevation Z. Okay, from here, Z units. Okay, and then all I see, I have to add up the volumes of those boxes from 0 to all the way to C. So so I take integral from 0 to C, AB Z squared over C squared dZ, which I can factor the constants. I can factor AB over C squared, and now I have the integral from 0 to C of Z squared. You follow me, guys? Are you with me? You can try to reproduce those calculations, and that's how you know you get it, right? So then what's this integral? This integral, for now, we haven't learned new techniques. We apply Riemann sums, right? So I just go and take limit as it goes to infinity. I use the right-hand rule to break it up. So the length of the interval is C minus 0 divided by n. So it's C over n, C over n. I factor out, I get C over n cubed, the summation of k squared. I know how to sum k squared. It's n plus 1 to n plus 1 over 6. I take the limit. I see that 2 survives. The C cubed survives and the 6 survives. So the answer is 2C cubed over 6. So the answer is C cubed over 3. And so AB over C squared must be multiplied by C cubed over 3. And I get ABC divided by 3, which is the volume of the pyramid.
Okay.
You see? So we figured that one out. Let's see if you can figure this problem, guys. I'm not sure if you want to try. It can take, maybe on first trial, can take some time. What about volume of circular cone? So you have a cone, and each cross section is its cross section is a circle. What object? What series of simple volumes am I going to use? What do you think? What simple volume can be used for which for which you can, if you can build up?
We use a rectangle for a pyramid.
Yes. What would you use for a circle?
A cylinder might be good.
Yeah, cylinder is good. Oh, so you know the volume of a cylinder is very simple. It's the area of the circle times the height, right? So volume of a cylinder is, and you can try to think why that's so simple, right? If I know the area of the circle, it's not simple to know the area of the circle. But if I do know it, it's area of the circle times the height, which is the volume of cylinder. So can you figure out, or try, guys, to figure out the formula for the volume of, oh, Sarah. Oh, you made a debut. It's so nice to see you.
Okay.
All right. So I want you to find the volume. Find the volume of a pyramid that has height capital H and base radius capital R. See if you can do that, or set up the procedure.
Do you have like a sketch that we could look at?
Okay. I mean, it reveals a bit, but
no, leave it. Okay.
All right, you can make your own sketch, right? The idea.
So you're saying we have a cylinder, or this way, downward, upward.
You have a cone. What's a cone? It's something that looks like a triangle that was rotated around the circle.
And you have a cylinder
inside, like a fool's hat, right? A circular cone looks like a fool's hat, or the hat that used to be that what do you call them? Heretics would wear before they were burned by the Inquisition, right? So it's like a long white cap, triangular. You don't have to finish the problem. I just want to see the problem set up as an integral that you would solve. You understand?
Wait, give me a sec. Can you give us like 2 minutes? How long?
No, no, take 5.
Professor, can you scroll down a little bit so I can see the answer, the question?
The question here. Good. Can you see it?
Yes,
If I
thank
scroll
you.
more,
No, that's
yes.
enough. Thank you.
Professor, can you talk? Can I ask you something in the chat?
Yes, you can ask me.
Just private. It's privately.
You can you know where you can send the message. It's easier this way.
Wait, should I send you a message through the phone?
Yeah.
Okay.
Most, it's already 17 people. I see some people decided to leave me once they voted. That makes me very sad.
I'm trying to figure out how to work this. Okay, I sent you a message.
Okay. Once it arrives. Okay. So I'm saying yes, but that depends on your interpretation, right? I think if I understood you correctly, the answer is yes. Okay.
Can I try giving it a shot or no?
Sarah, just give me one more minute, or is it time is up? I forget.
Okay. Wait, actually, I don't know if I'm right. I don't know. We'll see.
Okay, but yes, if you want to. So I think Alex 1/3. We got 1/3. 1/3. 1/3 should not appear before you took the integral, Alex. Hmm? All right. So shall we? So
Wait, this is an equation that I'm supposed to give you, right?
you are supposed to give me an integral. I mean, calculating it's already secondary and usually very simple, right? So more important than the calculation is to actually be able to realize that something is an integral, right? So yes, you see. So first, imagination. How do you imagine this cone? And you already said that the simplest pixel is in that case. Not in that case, just a stack of cylinders that diminish in size. Yes.
Yeah.
Yeah. So let's look at it, guys. Since okay, so here is how I view it, right? And I could have drawn many of them, but I imagine that if it's of height capital H and radius capital R, then you have a cylinder suspended, let's say at Z. That's the thin cylinder, right? That I'm adding at position Z. So I'm actually adding it from top to bottom, okay? So here I moved Z units. What's the corresponding cylinder? So I know it will have some radius little r and thickness dz. I will make them all uniformly thick. So for everywhere the thickness is the same, but it's very small, okay? So the thickness is dz. So what is r? So here I have a triangle. So I think that's what Joel mentioned. It's the ratio of r to Z is the same as the ratio of capital R to capital H, right? So I see two triangles, one big triangle and one smaller triangle. I need a formula for what's R in terms of Z.
I used different letters. Is that fine? Like
letters don't matter.
the concept
At the end, look at it. If I wrote that my question in terms of capital H and capital R, those are the letters that should survive.
Right.
If this little letter, little r, or you can call it v or the z, those letters cannot be part of your final answer because the question did not involve them, right? The volume should be in terms of capital H and capital R.
Right. So
okay.
That's what it says, right?
Yes, right.
Okay, continue. Sorry.
All right. So little r divided by z is big R divided by H, right? So that's what I wrote over here, which means that little r is capital R divided by capital H times Z. And then the volume, look at it, the volume of the cylinder is pi r squared, the area, times dz. So pi r squared dz, and then I convert in terms of Z. What's pi r squared in terms of Z? It's the same as pi multiplied by RH times Z all squared, which I factored out, you see. I factored this. I just took this and I squared.
Hold on. Can you redo that just quickly, the last part?
The last part is, so again, I have...
thus pi r squared times dz is equal to... Yeah,
Yes,
that one.
yeah. So I just plug in. R is this thing. I plug it in.
Yeah, I did
square.
that too, but
Right, so-
after that, I didn't get what you got.
Well, because then I get pi r over h squared z squared,
Yeah.
because I can distribute the square to both z.
I got it.
By the way, here is, notice that 2 has to do with, because the cross sections are 2-dimensional, right? So it's 2 because of that result, right? Before that, it will be z to the power of 1, because when we have area, the cross sections are 1-dimensional. Okay, so it's a pattern here. This is 1 dimension less than the object. So 3 minus 1, right? So this should always be followed. So it's pi r over h squared z squared dz, and that's the integral I get. Okay, pi r over h squared z squared, and then I can factor out all of them are constants except for z squared. So it's really the integral from 0 to h of z squared dz multiplied by a constant. And I know how to integrate this. This I can use Riemann sums. Yes, wonderful, Sarah. Yeah, you're good. Good, sir, right? And then that's what you get. You get pi r squared h over 3. Okay, and you can get this. You see, once you get this idea in your mind, you can figure out. Even when integral doesn't appear, it becomes natural to you. Understand? Here is a question. You don't see it, the question as an integral. Nobody tells you to use integration, but you realize, oh, it can be simplified by, let's say, questions about work or energy. If you have a piece of rope, let's say, and then you hold it like this, and then you drop it. So so the bulb or the bottom of the rope will fall like this, right? And the question is, let's say, what is the change in potential energy? That will naturally be an integral, because you have different changes in potential energy because different pieces of the rope fell at a different distance. You understand? So right away you think in physics, oh, that's an integral, because it's just a summation. It's what happened to this particle and that particle and that particle, which moved a different distance, and that right away is part of your thought process. Good. Wonderful. So that was just an illustration of what what those techniques can be used for. Okay. Now we will focus on some shortcuts first. Good. So that would be lecture 5. And here, and some of you that took calculus before might already know those shortcuts, but not know why those shortcuts work usually. So up until now, the way we would solve an integral of some function fx dx from a, b, we will just convert it to, say, the right-hand sum and take the limit. Now, in essence, I would look at this. I would have to take this painful process of writing the summation, a function f, a plus k, b minus a over n, b minus a over n.
That's a lot faster.
And a lot of process, you see, so to figure out what it is. So for example, if I had to calculate the integral from 0 to 2, 3x squared dx with the information I have up until now, up until what I taught you, I would have converted it to this Riemann sum, right? You see, this means I divided the interval from 2 to 0 into n parts, and I take the limit of areas that add up on those parts. So it's 3k times 2 over n squared, 2 over n. I factor everything out, and the summation of k squared, I convert the summation to its closed form n plus 1 to n plus 1 over 6, and I take this limit, right? So this limit is 3, 2 cubed, 2 over 6, 3, 2 cubed, 2 over 6. That's from early material that I can take those limits fast, right? But I would have to go through quite a long process to get at this 8. Now, you see, you might observe the following, right? So there is going to be this shortcut that will be relating the process to anti-differentiation, right? So imagine you're dealing with an integral from a to b fx dx like before, and imagine that you can guess a function that's an antiderivative of this little f. So then what would end up happening is that it's the antiderivative evaluated at this point minus the antiderivative evaluated at this point, okay? They early on in the study of calculus noticed that this is happening. So for example, right, here is the same problem that we solved using Riemann sums, 3x squared. You have this integral from 0 to 2, and then you have this notation, which just talks about antiderivatives. The reason, again, we use the same notation is because you can see those two things are related. If I'm able to find an antiderivative, in this case, it's x cubed plus c, correct? So I just take x cubed. I can take one instance of it. Any antiderivative will work. I take x cubed. So then I evaluate x cubed at 2 and subtract x cubed at 0. So it's 2 cubed minus 0 cubed, and again, I get 8. You with me, guys?
Not that bad.
So if it basically, procedure-wise, instead of going through Riemann sums, I can find antiderivative, evaluate antiderivative at top number, subtract antiderivative at bottom number. You see? And that gives us 8. Let's see if you can do it. Let's see if you can do it. You see, I explained very little yet. And now you are going to try to solve, let's do A and B. Some of those things you will be right away stuck by Riemann sums. Let's say you would not be possibly able to find the Riemann sum for a root of x. You would not be able to simplify the Riemann sum to see the limit. But see if you can use this new trick to solve A and B.
Professor, can you go a little bit up so we can see the example you show us?
Right, here. Can you see the example or should I go a
Yes.
little? Okay, good.
No, that's good. Thank you.
Yeah. So solve for now A and B.
Professor,
Yeah.
after we so you see over there on the for the example above, it says for instance, yada yada, we obtain so and so, right? So for the example A, what do we do after we obtain that figure with the
Obtain the
x above?
simplest, basically obtain a simple antiderivative, the simplest you can think
I
of,
got it.
and plug 2 and subtract from it plugging -1, okay? Just like
Can I
over
see
here.
what I got?
For A,
Yeah.
I want to be sure that, just a second, guys. Are you ready for A or should I wait a little longer? Yes, or one person wants to jump forward, or do you want to wait to think of it a little longer? Let's do this. Okay, yes means solve. Wait. Okay, so
wait.
let's wait. Okay, wait. Try to, if you solve it correctly, try to solve more. Okay, solve
Yeah,
as many as you can, and we'll check.
We're just trying to find the shortcut. That's it,
Well,
right?
we are trying to use the shortcut to solve those problems, right? So the shortcut, as I explained, is here. For this function, find antiderivative, then plug top number and subtract plugging in lower number.
Oh, that's how. Okay.
You see what I did here?
Yeah, I didn't finish. I didn't
found
finish
x cubed. I found x cubed, then I plugged
Right.
2 into x cubed and subtracted the bottom number 0 for x cubed.
Yeah, so it doesn't make sense for me to do it that fast then, because I didn't do it all the way then.
Okay.
Give me a minute.
Professor, I'm gonna have to leave a little early today, around 7. So is this all recovering today? Or
Well, all is what is all? So we're doing those questions. Then we are doing average value. That's yeah, that's what we do today, I think.
Okay.
And I will finish with fundamental theorem of calculus and other things on Thursday.
Okay, thank you.
And whatever I wrote here, I already have posted to my website.
Website? Okay, so I'll take a look at those. But I'm still gonna be here for another 4 minutes, so 3.
It's too bad, Sarah. You decided to hide. Why did you showed your face like a swan for one moment, and then whoop, you disappeared.
Yeah, I had to go get something.
Okay.
Professor, can I give it a shot now?
A shot? Oh, many people want to shoot me. So go ahead. What do you want to say?
So for I got for the shortcut was 1 over 4x to the 4th minus x squared.
Yes, correct.
And then for the next part is you're going to plug in 2 into the equation, and you're going to add that, plus you're going to add that to, you're going to, how do I put this? So you're going to get 1 over 4 times 2 to the 4th minus 2 squared, yeah? And then you add that to 1 over 4 minus times negative 1 times negative 1 to the 4th minus 1 squared.
When you say add, I just have to be sure. Okay, so here is how I wrote the procedure, guys. Okay, so you said, Joel, correctly, right? It's 1/4 x to the 4th minus x squared. So what I do is this. You see, guys, I look at it, and that's why you have this indefinite integral, right? Because somehow the indefinite integral, the antiderivative, is related to this problem of finding, let's say, area under the curve. Yes. So I take this, and I create, this is the antiderivative, or an antiderivative. And then I write a bar, and I write -1 and 2, which means I first plug in 2, and then I put minus, and in parentheses, I plug in -1.
Why minus?
Well, why plus? Why anything, right? This is not explained here. I'm just giving a shortcut. Usually, I don't like, actually, my personal predilections is I prefer to understand before I see what works. But most people first want to have a feel of how it works, and then they want to understand. Okay. So I did not explain why my minus, right? I could have written multiplication or division or none of those procedures.
I wrote plus because of the, okay, continue.
Right. So the way it works is that you put a minus, right? So you put this expression at 2 minus this expression at -1, and then you simplify. What is this? This is simply 0. You see this? 1/4 times 2 to the 4th is 2 squared minus 2 squared is 0. So first part is 0. The second part is going to be minus. I have this minus. This becomes 1/4 minus 1. So altogether it becomes 3/4. Good. So that was problem A.
Can you explain the minus part?
Later, I can, of course, but you see, here you are too bothered by the minus. Why are you not bothered by the entire procedure? Take care, Sarah. Have a good one. Hope to see you
Bye.
on Thursday.
I remember doing something like this a long time ago, though.
All right. I say so. Where are we? So let's move on. Oh, okay, good. I was worried some people are not here, but some of them are still here, even though I have 15 people. So what about B? Okay, and B as quickly as you can, guys. It's training, right? Now it's for root of x. Have you done this? David, do you know the solution for root x?
Is it 1 over, is it x to the 1/2?
So David says 39. Oh, well, no, I think it's not an integer, if I'm not mistaken, right? So first of all, what do? You see this root x?
Yeah. Okay, continue. Sorry.
Yeah. So you see root of x, guys.
I'm gonna mute myself.
You see root of x. And let's see, where is root of x? Root of x, we convert to x to the 1/2, yes? It's x to the 1/2. And x to the 1/2 is when it's converted, when I take the integral, is x to the 3/2. But don't scare the child, you know, she's still young. She hasn't seen all the horrors yet, right? So it's x to the 3/2 that I convert, yes? And then what? And then you see the other derivative is 2/3 times x to the 3/2, correct? You agree with me, guys? And then I plug in 9 and I plug in 1. So plugging in 9, it's 2/3 multiplied by 9 to the 3/2. 9 to the 3/2 is the same as 3 cubed. And because I divide by 3, it's now the same as 2 times 3 squared, which is 18.
I think, I'm sorry to interrupt again. This is the last time I'm going to talk.
No, don't worry. It's good that you talk. I just want to be sure that others, you know.
So because I remember you mentioning once about the sum of them. That's why I was saying, that's why I put a plus when I do that.
Well, again, yes, sure, Dave. What it is, guys, and it's be very careful here. I'm just giving you a shortcut. What maybe you said plus because what is the immediate procedure you think about? It's a bunch of rectangles whose height is root x times width dx that you add up from 1 to 9, right? So originally, naturally, you think summing rectangles, but I'm saying that the shortcut involves this strange procedure. You find antiderivative of this function and then plug the top number minus antiderivative at the bottom number. Okay. I mean, there is no reason why you should say yes, sure, that makes sense right now, right? You can try to think about it, but it's not trivial. Why?
I'm just saying okay at this point, Professor.
Right. At this point, and you don't have to believe me. Again, this is called fundamental theorem of calculus, which means it's an extremely important result. It's not supposed to be so immediately obvious. For this to be immediately obvious, you have to be extremely clever. If you never saw it before and see, oh yes, that's the case, it's a sort of extreme cleverness. You might have seen that this result is true if you had some enough experience and thought about it, but it's not a trivial result. It's already it's somewhat a deep result in calculus.
Okay.
Okay. So you take a derivative, plug those values, you get 18 minus 2/3. Good. And next, guys, continue. So do the other problems as quickly as you possibly can. Your goal is, again, using the shortcut, okay? Using shortcut, figure out C, D, and as many as you possibly can here. So guys, how is it going? Ready? Yeah. So so how do you solve question C?
Anyone?
Okay, so let's see. 40. So first thing, so Melissa got 96 for C, and C is the solution for it. So let's see. So first, I would combine, right? Be careful to combine it. So you have t to the 1/2, multiply it through. You have 4t to the 1/2 minus t to the 3/2. Yes, guys.
Yeah.
That's what Joel wrote. Okay, so then what you do then is then you guess the antiderivative. What's the antiderivative of 4t to the 1/2? It's 8 over 3t to the 3/2. Correct. The 3 has to come down, and something must cancel the two, right? So you just get quick with this thing. Understand how I think? I just look at t to the 1/2. I guess that its antiderivative is t to the 3/2, but then I know 3/2 will count down, so I have to cancel them out, so that 4 remains. So I pretty much write 2/3 here and then multiply by 4. So 4 times 2 is 8. That's how I know this answer. Okay. And similarly for this number, I will see that it's t to the power of 5/2, and here I have 2/5. Yes. And so what happens is that we get 64 over 3 minus 64 over 5, right? Because, well, when I plug in 4, square root of 4 is 2. 2 cubed is 8. 8 times 8 is 64. Here I have 4 to the power of 1/2 is 2. 2 to the power of 6. Again, we get 8. So we have 64 over 3 minus 64 over 5. Good? So that's just a calculation. Now, how about D? Come on, guys, quickly, so we can move and finish today's lecture. So do DE as fast as you possibly can. If you can do F, that would be extremely nice of you.
Does that say pi over 4? Yeah.
Yes, it's pi over 4.
Okay.
All right, Batel. So that's for what? For D? For D, Batel, or for what, secant squared? And then also simplify as much as you can, right? So we have secant tangent. Is the antiderivative of secant tangent secant squared or something else? Be careful, right? What derivative produces secant tangent? Correct, Joel.
Awesome.
Yes, but finish it. I need it at the bounds, right? It's a definite integral. Okay.
I mean, okay. Fine.
Okay. And so here, okay, let me show you how to solve this, as we need to move on. You see, guys, you just have to be good at antiderivative. So what's an antiderivative of secant tangent? Secant beta is the antiderivative, yes? And then evaluate from 0 to pi over 4. So plug in pi over 4, you get root of 2. Plug in 0, you get 1. So it's the secant of pi over 4, which is root 2, minus secant of 0, which is minus 1. So those identities you can know. It's not so hard to know them, okay? Now, very quickly, what about the next one? E, secant squared. What do we do then?
Isn't that tangent?
Yeah, I was just gonna
Yeah,
ask.
it's tangent. Correct, David. So it's tangent. Okay. So it's tangent at pi over 4 minus tangent of 0, and Sam
That's 1.
says 1. Correct. It
It's
is 1. Right. Let's just look at it again, just to be sure. Right. So here tangent, because I know a derivative of tangent is secant squared. I have pi over 4 and 0. I plug those in, and I get tangent of pi over 4 is 1. Tangent of 0 is 0. So the answer is 1. Remember, guys, right? Make it organic. Understand why those work. Why I have the trigonometry notes. You can use them. I haven't yet written the first part, but some of you attended the lecture when I did it after class. Okay, so trigonometry, as we know it in this class, is not terribly difficult. Yeah. So. Yes, so here is now question F. Can you solve question F?
Yeah, I don't know.
F, why not? What would you do, guys? Right? Look at F. What does it feel like we should do here? Seven? Why 7? It would not be that simple.
I switched it to v to the -4th and then multiplied.
It doesn't
And then
matter.
combine
Sure,
them.
that's the same. That's fine. But so what do you get when you combine it? So I see answers like 6 or 7 or things like that, and they cannot right away. You can see it cannot be the answer. So what do you want to do here, right? Okay.
Is it
Maybe make it into 2 fractions,
Fine.
like
That's
2 separate.
Cool. Wonderful. So make it into 2 separate fractions. Yes. Get rid of the denominator. Sure. That's well.
Yo, I'm lost.
Okay, we'll get there. You have to make the expression presentable enough so you can figure its antiderivative.
Can you subtract the exponents?
Well, if you mean by it something correct, then yes. It just the way you said it might be interpreted incorrect. Subtracting exponents, it's vague.
Is it 1 over v plus?
Correct, Abdul. And what you were doing, it's also good.
Wait, but how did he get 3? Oh, good.
It's very simple. I take when I divide, I divide this part by v to the fourth and this part by v to the fourth, and this is what I have. Again, guys, don't feel pressed if you don't feel you had enough time. It's only because we have a very short hour, right? I would have been sitting here for 2 hours if that was the matter here, right? So I divide by v to the fourth, I get 1 over v. I divide by v to the fourth, I get 3v squared. Okay, so we have this. Good. So it's the integral of 1 over v plus 3v squared, correct? Now please integrate and tell me what is it that we get. So you have to find antiderivative for this expression to do it using the shortcut. If you tried,
can you scroll down a little more?
Here, can you see it now?
Yeah.
Yeah. So you need to find antiderivative to apply the shortcut, right? What's the antiderivative of this expression? Exactly. Exactly.
Is it this? Okay.
Yeah. So what's the antiderivative? It's the antiderivative of 1 over v is ln of absolute value of v. The absolute value will not be required because the numbers are positive here, right? But it's ln of absolute value of v plus v squared, the antiderivative of this part. So if I plug in 2, it's ln of 2. Plug in 2 in here, so it's ln of 2 plus 8. And then minus the expression where you evaluate at 1. ln of 1 is 0, right? Because ln refers to a power. To what power must e be raised to get 1? The power is 0, right? So it's 0 here, and then so we subtract only 1 cubed. So it's ln of 2 plus 8 minus 1, which is ln of 2 plus 7.
Okay.
Good. Next question is this one. What about that?
Oh, what am I looking at? Can you look at my text?
Yes. Correct.
Okay.
Correct. Abdul, 8 tan inverse, correct. So All right, so the answer is simply integrate tan inverse to tan inverse, and then you have tan inverse evaluated from 1 over root 3 to root 3. If you remember, this is this triangle. So we have pi over 3, pi over 6. They correspond to root 3 over 2 and 1/2. And so you can observe, for example, that tangent of pi over 3 is root 3, because you just take this number divided by 1/2. So tangent of pi over 3 is root 3, which means that tangent inverse of root 3 is pi over 3. That's what you get over here. And if you look at pi over 6, tangent inverse of 1 over root 3, this over that, 1 over root 3 will be pi over 6. So it's 8 times pi over 3 minus pi over 6. Yes, so 8 times pi over 3 minus pi over 6. And the answer then is simply, you can just simplify it, it's 4 pi over 3. And now the hardest of the bunch, question H. So the function is 4 minus x squared and 2. And the integral is from -2 to 2 of fx dx. What is that integral, given this information? Okay, do your best.
Professor, I messaged you.
Mm-hmm. Correct. That would be the best approach, since we have different functions. So let's do it to move to the next topic. So very simply, so you have two integrals, right? -2 to 0, because the function has one formula between -2 and 0, and another formula between 0 and 2. And remember that property of integration, that you can break it. So then first part is the integral of 2, which I don't even need to do any integration procedures. It's just 4, because length is 2 times height 2. So it's a rectangle of area 4. The second part, I find antiderivative of 4 minus x squared, which is 4x minus 1/3 x cubed. And I put in those bounds. And I solve, and I get some number. Good? So now guys, maybe it becomes say, okay, can you do one more? Can you calculate what's the value between, what's the integral between -1 and 1 of 1 over x squared? That's the antiderivative, except you forgot, Joe, to put a -1 next to it. Right, because the 1 over x squared, right? It's x to the -2, so good. How are you doing, Batel? You're good? No, that's what I see. I see fire in your eyes of sorts, right? My brother, you know, when we drive around, he looks at houses and they say, "Oh, so many doors, so many houses, and you never know which one leads to hell. How many hellholes are there?"
How does that make sense?
-2. Oh, how does it make sense? Okay, okay. So
That can't, because you have to get some positive for the area, or
well, let's see.
not the
Right?
area. You have to get. You have.
So we can try this shortcut. We take antiderivative of 1 over x squared, and it's correct. It's -x to the -1. Yes.
Yeah, but then when you do the math, when you try to do the shortcut, you get -2.
Right, and when you do the shortcut, you get -2. Is this the right answer, guys? -2 is the right answer for this problem.
But when you I don't know if I'm pushing too far right now. I don't know. I don't want to push boundaries. I don't want to sound like, you know, someone.
This, by the way, involves pushing boundaries. This is called improper integration. So, so you see, you look at it, and
Wrong.
correct, and you see that that it looks like well, it looks like I'm just adding up positive area, right? So it doesn't look like this is if I do it by, so to speak, by observing it. I expect possibly a positive area, right? Maybe infinity. I'm not sure, right? Well, I am sure, but you know, right? So you're stuck in. Basically, this process is not going to lead. The shortcut is not going to lead to a correct answer. And again, guys, that's what I want to. Yes, that's another story. The question is not how to get an answer, but the question is. This is very important, is that you use the right, that you understand the tools that you are using. You understand, if you're just mechanically doing something, there is no reason why you should be surprised that the results you obtain are incorrect. Right? You have used this tool incorrectly. So that's again why I advocate against memorization. You want to understand what you're using. If you have no choice for a moment, here is a tool. You kind of do whatever you do to survive, but in essence, you strive to understand the tool if you actually want to get meaningful conclusions out of it. Okay, and that's pretty important. Again, a person. I mean, there are always backgrounds to things, correct? Backgrounds to other stories, but truly, for mathematical reasons, a person discontinued speaking to me. That's how it works, right?
I don't get, why did someone block you?
Because they misunderstood what I have to say, because they, in a sense, they interpreted a mathematical result incorrectly. Understand? And that's what that happens if you and that involves implications, right? So they imagine that what I'm saying is something very, very offensive to them because they misinterpret the mathematics. Because you can say many things mathematically. If you're interested, I'll show you examples, right? So once you know enough of it, you can say many things mathematically.
Yeah,
this is the problem to a prior problem to at least to one of the ways I think of the fundamental theorem of calculus. You want to understand why the shortcut works. That's the fundamental theorem of calculus that you try to understand. And that, as I mentioned, is conservation of energy. When you say no energy is created or destroyed, this is only a mathematical ideation. When you say that, you are saying that fundamental theorem of calculus holds, at least in the one-dimensional version of this energy principle. Okay, so it's very, very fundamental, right? And here is a first problem that we need to tackle, and this involves your intuition. Very few calculations, but just what you have in your heart. So imagine I give you this task, right? So because it's still calculus, it's a one-dimensional task. So here is a landscape from A to B, and you have to estimate. So you see, you're walking on this landscape. how high is this landscape on average, right? What's the average altitude over the sector A to B? Does the question make sense, more or less? So let's see if it does, right? So I think of it as a construction site person, and he digs into, maybe you're a miner, right? And you want to dig to the ore, which happens to be the x-axis. That's where the gold is, and you want to know on average how deeply you have to dig. Okay, so how would you figure out? How would you figure out what's the average? If somebody assigned, some construction manager assigned the task for you to figure out the average altitude over the piece A to B, what would you actually do? You understand my question, yes? So you are tasked to figure out the average elevation here. You agree that the elevations at different points are not the same, but what on average is my elevation? That question, maybe it makes sense. I'm not sure if it does make sense to you, but does it? Right? You can ask what's the average height of a person, right? So you obviously do not match the average height. You are either above it or below it, right? It's impossible to actually match it precisely. Right? The number you obtain for average, it's impossible to match precisely. So my question is, what is that average? How do you obtain it, and why? Any ideas?
Do you want to take? Can you?
Can I explain? You mean?
No. I'm trying to.
If you, here is my hint. Okay, let's say you have 30 people. 30 people. How would you find their average? Let's say I task you. You're my lab assistant, or I'm not sure what you are, and I task you to find the average height of the people in my class. There are 30 people. What would you do?
You measure all of their heights and then you divide it by 30. Exactly.
So here you understood. Now here I ask you a very similar question, right? I ask you to find the average height of this landscape.
So then,
what do you do? Yes, Sam, go ahead. Or Melissa, I have an idea, but I feel like it's wrong. Melissa, and anybody, don't worry about wrong. If Sam was speaking first, I want to hear what Sam had to say, and if Melissa, you would contribute, I would be happy. Yes.
You find a certain amount between each point between A and B, and then you find the height at each point, how deep it is at each point, and then you add up and divide it.
And divide by what exactly?
How many points you have.
By how many points you have. So so in some sense, yes, why not, right? That's somewhat, guys, there is not so much difference between this question and averaging people. Imagine that people are very thin. They're like those sticks, and there are many sticks, infinitely many, in fact, sticks standing between A and B. And you have to figure out the average, right? The problem is you cannot calculate all the infinitely many sticks, right? But the function is continuous. And notice that sticks that are nearby are essentially of the same height. Do you agree? So people that are standing very close together, in this case, are essentially of the same height, right? So those are like sticks. So what do I do? Methodically, can you divide? Yes, but in fact, you are absolutely correct. Beautiful, right? Let me try to explain slower why that's exactly what you're doing. So what I would do is methodically, I will add up the heights, right? But I will take them at an interval. So I imagine in the construction site, you walk a little bit, and then plunge in this measuring stick, then walk a little bit farther and plunge in, and walk by same amount, equidistant segments, right? And where those segments are, the steps are very close to one another, okay? So this is what I describe. I take n sample points, very much like statistics. I take x1, x2, xn, right? So the first sample point, I take from A at an interval b minus a over n, right? So I move by one increment. Let's say this is one increment. I take my first sample. Next, I move by two increments and I take a sample. And finally, I move by n increments and take the sample. Since I took n samples, I take the average of the sample, correct? So the average is 1 over n. times the sum of the elevations of the samples. Does it make sense? You see, I sum all the samples and I divide by n. Yes? Good. So we have this and we divide by n. And how do I obtain the xk? I already mentioned, right? So the summation is fa plus kb minus a over n. This is the point at which the sample is taking place. Yes. And you look at this expression. What does this expression remind you of? And of course, you want n to be very large, because if you make very, very small steps, if the step is very small, the elevation has not changed too much, correct? So how do you, what does this remind you of? First of all, do you see that you want to take limit as n goes to infinity? And goes to infinity because you want to take more and more points in your sample and them to be closer and closer. Then you're approaching to the actual average. So what does this limit remind you? That's the average. If average will be limit as n goes to infinity of this expression, correct? What does it remind you of, please? Look at it, guys. You see, it's now a matter of recognizing. What does this remind you of?
Riemann sum.
Riemann sum, which means what? Converted to another expression, converted to an expression that you have seen before. That's correct, but except not a perfect Rn integral. Okay. Look at it, right? So I move the 1 over n over here. Look at it. It's just a distribution. It's one number multiplied through a sum, so I can move this number in, and this looks like Rn essentially, right? But what fails to look like Rn? Look at it. Something should jump into your eyes and tell you, not quite Rn. What is that?
You don't times it by b minus a divided by n. You times it
Exactly.
by 1 over n.
Precisely, right? So this is incorrect. It should be b minus a, right? And I modify it. I put in b minus a here, and I put a b minus a out, right? So they can cancel out, right? So I see 1 over b minus a, 1 over the width of the interval, multiplied by a perfect Riemann sum. So when I push a limit, I get 1 over b minus a, the integral from a to b fx dx. You understand? So you now see that integrals and averages have very much in common, right? Average and integration is very much in common. Right. So now, guys, this is the ultimate test. I hope you will stay to finish this problem. So without doing any calculations, okay? Determine this limit. Limit as h goes to 0, 1 over h, integral from 0 to h, x squared plus 2 dx. You look at it, and right away, if you have the right instincts, right away you can see the answer. What's the answer? So 1 over h, integral from 0 to h, x squared plus 2 dx. So again, what you have to do is recognize what this expression is talking about.
It's just going to be 2 because it's 2, right?
It's right. It's 2.
Because,
But why is it 2?
Because if you what is it called? If all the values of f of x, right, by 0, would make that 2.
Yes. And why do I consider so that's good. That's good. So look what happens here, guys. Right? I push h close to 0, which means if I for a moment ignore this h, when I ignore this h, right? When I ignore this h, what this integral is talking about is the average, right? So this is the average of this function, because look at it, the function has width h, right? And I divide by 1 over h. So this part just talks about the average of the function, or x squared plus 2. And because h is very small, we are averaging near 0. And this function is continuous, do you see? So all values essentially are like 0 squared plus 2. Because what happens here, it's like I'm moving to a country. That's really what happens. You move to, let's say, France, and suddenly you find everybody speaks French, right? So, and maybe the transition, you would actually see the transition is gradual. People, let's say, at the Polish border, that as it becomes German border, they speak Polish, German. And then as you move towards the border, they begin talking more that one language over another. I was born near a border by Russia. I speak Russian, although I was in Ukraine, right? So it's just you move over there, and I don't understand Ukrainian actually, right? So it's as you move closer to one border, you transition in your language as well. So this is again 0. Do you understand why the answer is 2, right? Because essentially it's like 0 squared plus 2 near where h is small. That's the average. Okay. Next question is B. What's the average for sine x over x? What is this? So we have function is sine x over x if x is not 0, and it is 1 when x is 0. This is the function I integrate from 0 to h. What is this limit? Okay. David, you are right, David. It is 1. What do you see immediately? It's 1. Look at it, right? This is the average of essentially this function, right? So I see 1 and I see sine x over x. And actually the limit as x goes to 0 of sine x over x is 1. So the function is continuous, right? So what I'm seeing is essentially numbers that you cannot distinguish from 1. If you zoomed in, the numbers will do near let's say if h is very, very small, this is the numbers you're seeing, this function looks like a horizontal line essentially, right? Nothing in nature is perfectly flat or anything, but this looks essentially like it's flat, like it's horizontal, right? So the answer immediately is 1. Isn't it cool, right? You see right away because you interpret, you see, oh, it's the average, and actually you can solve very interesting integrals this way, but of course much smarter type of stories, right? You understand what it talks about, and you have another way of calculating it, okay? Or another way of realizing the answer. What about this question, guys? So C. Tangent of 5x over x. This is the limit. See if you can calculate it, and be careful. Look at it carefully.
This time it's from negative h.
Right. So look at it carefully, and again, still you can figure it out perfectly. But L, very, very good, but be careful, right? One thing, look at it very carefully. What's the length of the interval?
Oh, it's 2, so it's 5 times 2, so then it's 10.
Yes, good. So you see, you are right, but it should be a 2 on the bottom, right? This width, to be an average, this is, the width is 2h, so I have to divide by 2h. So there must be a 2, and I multiply it by 2. So other than that, you are correct, but the answer is 5. Because look at it, okay? This is tangent 5x over x. That's roughly 5, and this is 5. So the function is averaging to 5, but this is not average. This is average divided by 2. So you must multiply it by 2, right? So you have to put 2 here and 2 here, and that would be 10. Good. Now, final question is this D. Can you do that one? E to the sine of 6x over 3x. If x is not 0, 0 otherwise. And this is the function, and I ask you to calculate this limit. Mattel, let's see. So it's 3. Beautiful, but wonderful. Beautiful, right? It's 3 times e squared. And notice that in this case, we have an outlier, 0, right? So we have an average. Exactly, truly. I'm very, very proud. So look at it. What happens is that we have an average here, right? Once I put a 3 and correct, multiply by 3, essentially I have an average. And in this average, notice the function isn't continuous, but I have a lot of numbers that look like e squared, right? A lot of numbers that look like e squared, and one number that looks like 0. It's like, imagine you have a billion e squares and only 1 0, so it doesn't matter. It's like you have in Scandinavia, you have, let's say, everybody is 7 feet tall except for one person who is short, right? It doesn't matter. That short person is not going to change the average because it's just such a slight difference, right? That doesn't weigh much compared to the others. So integrals are very insensitive, like me, very insensitive to outliers. Okay, to outliers, it's as if they don't exist. Integration just looks at a function that is not entirely continuous and sees as if it were, right? So that's if you understand this, possibly it can be made even simpler. I'll explain it in 2 ways. The fundamental theorem of calculus. Okay, so more or less the lesson for today is over. I stop recording. If you want to see some questions, again, it's silly, but the questions I show, stories that I show about, so probability theory in stories, right, and relating it to integration. So I'm stopping the recording.